Hi there. This is a descriptor of a nucleophilic substitution reaction. A nucleophile donates a pair of electrons to a deficient site on a molecule, creating a new bond and causing another group to leave. Let's break down this descriptor a bit. First of all, what's a nucleophile? When I think of nucleus, I think of something positive. So a nucleophile is a positive liking substance. Something that would like a positive would be a negative ion, an anion. So hydroxide, chloride, cyanide, they're all examples of nucleophiles. The other thing is nucleophiles also have electron pairs, and you can find those present not only in ions, but also in molecules, in things like water, ammonia, alcohol. All of them have an electron pair. This pair is attracted to an electron deficient site. Let's look at an example of a halogenoalkane. The carbon-chlorine bond is very polar. Chlorine has a greater attraction for electrons, a higher electronegativity. It would pull the electrons closer to it, making the chlorine slightly negative and the carbon slightly positive. Because carbon lost the electrons, we would call it electron deficient. So our nucleophiles are attracted to that particular carbon, the one that I've shown here with a slightly positive charge, and causing another group to leave. Well, when my OH group, which I used for the example, takes the place of the chlorine leaves. We call it the leaving group. So we'll begin with a nucleophile that's an ion. I've chosen hydroxide here. The first thing is that a pair of its electrons will be drawn to the electron deficient site, that carbon. Simultaneously, the carbon-chlorine bond breaks with both electrons moving to the chlorine. I've used here a double harpooned arrow to indicate the movement of pairs of electrons, not just one. This will then be the product of that reaction, where the hydroxide is now connected to the carbon chain and the chlorine has left. Chlorine will possess a negative charge. The reason I know that is balancing. If I consider a charge balance, on the left-hand side, the molecule has no charge, but hydroxide has a charge of -1. So the total charge on the left side is -1. The total charge on the right side must also be -1. So the alcohol is neutral, meaning the chlorine must be negative. Here's what the overall equation looks like. You can see here the pattern of substitution, where the chlorine and the hydroxide have switched locations. Now let's take a look at the reaction of this halogenoalkane with a molecule. In this case, I'm going to use water as my nucleophile. So as before, the pair of electrons are drawn towards that carbon, and the pair of electrons connecting the carbon and chlorine leave. That would lead us to this state. Now, the chlorine we know is negative because it's taking 2 electrons from the bond, but the residing molecule must possess a positive charge. Again, consider balancing the charges. My original nucleophile, water, and the chloroethane have no charge. So the total in the next diagram must also have no charge. I know chlorine has a -1, so therefore the remaining molecule must have a positive charge. So there's one more little step here to happen, and that is the electrons that are present in that oxygen-hydrogen bond. Both of those will move towards the oxygen to make the remaining fragment neutral, and the hydrogen will then be positive. That positive hydrogen will then join the chlorine to make hydrogen chloride. So here's a look at the overall reaction in this case. One of the ways to differentiate the two is if the nucleophile is an ion, the leaving group is an ion. And in a similar fashion, if the nucleophile is a molecule, the leaving group must be a molecule. Let's take a look at a multiple choice question. Which of the following best describes the nucleophilic substitution of 2-bromobutane by ammonia? The first thing I note is I'm using ammonia, which is a molecule. That must mean my leaving group must also be a molecule. So therefore C and D are possible. To differentiate between these two, let's do a quick count of hydrogens. So in my reactants, the molecule with the bromobutane has 9, and there's 3 in the ammonia for 12 hydrogens. I then count the hydrogens in C and in D. And I can see that C has too many hydrogens in it, so my resulting answer must be D. There is a follow-up video to this topic for students taking higher level chemistry. Thanks for watching.